microscopic medicine, the story of smaller is unfolding on a vastly accelerated time frame. In fact, scientists are on the verge of realizing a 21st century version of the Fantastic Voyage story. They're developing microscopically small robots that travel into the body's deepest reaches to diagnose treat, and even destroy.
What?
That's a robot?
That's a robot.
It's like a splinter.
Well, this is a micro-robot. We use them to help perform surgeries on the eye or inside of the eye.
The device is only 1/100 of an inch wide, small enough to fit into the needle of a syringe, like the tiny sub in Fantastic Voyage. But the similarity ends there. This unmanned device is designed to treat a type of blindness caused by blocked blood vessels in the retina, the tissue where images are formed. And little propellers and some kind of knowledge to know where to go in the eye. I have a hard time believing that.
That's right. So the way we energize this is we use externally generated electromagnetic fields. So basically, it's a magnet.
To make the device small enough, Brad had to abandon the idea that robots have to be mechanical.
Copper-colored thing here.
Instead, he focused on finding a material that would let him eliminate bulky moving parts. He chose two elements, samarium and cobalt. Combined, they form a material highly sensitive to magnetic fields. A swimmer the size of a bacterium would never be able to get around using flippers or the breaststroke, because at that size, the friction from the water molecules becomes a major drag. For a long time, scientists couldn't figure out how bacteria were able to swim. But eventually, they discovered the secret. The tail, or flagellum, seems to move back and forth. But viewed from another angle, it's clear that it moves in a totally different way. Corkscrew tail.
A corkscrew tail.
Brad and his team have developed corkscrew robots that mimic bacteria.
Bacteria like E. coli and Salmonella have developed these flagella that twist.
This part is the flagella?
This flagella twists through the liquid, just like a corkscrew going into a bottle of wine. So instead of propelling itself or using its inertia, it's actually kind of cutting through the fluid.
It's almost pulling itself instead of pushing
It's pulling itself in a sense, like a screw going into wood or something like that. It's a completely different material interaction.
They use the same samarium cobalt material and magnetic fields to set them in motion. So it's literally like drilling its way through that liquid.
Drilling its way up.
Wow. This is the biggest one. The smallest one is only 30 microns long. That's 30 millionths of a meter. About a third the width of a human hair.
So now, just in the last few years, we've actually been able to build small things of a similar size and shape to real bacteria that swim just like they do, potentially deep inside a person's body.
The magnet-driven robots in Brad's lab, the iBot, the FlagellaBot, and even a soccer-playing robot that his students created, are each no bigger than a dust speck. Brad's learned to modify his robots to overcome the physical obstacles in the microscopic realm. But he's only scratched the surface of the strange properties in that infinitesimal world.
An atom is actually a fraction of a nanometer.
Chad Merkin is an explorer and pioneer in this weird realm, the nano world. You keep saying you're building things on the nanometer scale. I don't even know what a nanometer is. So this is a meter, this is a centimeter, this is a millimeter. Is this a nanometer? What's a nanometer?
Let me try to illustrate it for you. If we shrink you by a factor of 2, you're about the size of a small child. We continue to shrink you by a factor of 2 4 more times. You're about the size of a golf ball. We go to 10, you're now the size of an ant. We keep going another 7 times, and now you're about the diameter of a human hair. That's roughly what we can see with the naked eye.
Even after so much shrinking, I'm not even close to the nanoscale. Cut me in half 5 more times, and I'm the size of a